Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Today, Science Max is all about sound. We bend the power of sound to our will by making the loudest sound we can.
A subwoofer.
Subwoofer.
Make cornstarch mud dance, glasses break, and things vibrate. It's the sounds of science. Today on Science Max, Experiments at Large.
Greetings, Science Maximites, and welcome to... Can you hear me? Greetings, Science Max! You can't... Oh, hold on a second.
Greetings, Science... Yeah, that's much better. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. Today, we're going to be talking about sound. Sound is all around us. We use it every day, but what is it really? Sound is energy. Let's say that this is the... No, stay. Stay. Okay. That this spring is the sound of my voice. When I make noise, it travels away from me in a wave. One air molecule vibrates the next air molecule, vibrates the next, and it looks like a wave. And when there's a little bit of energy, the wave doesn't move very much. Science. But when there's a lot of energy, the wave moves a lot. Science! What do we do? What do we do to make sound louder? This is the Science Max theme song. But it's not very loud because the speaker on my phone isn't designed to make super loud noises. So what we're going to do is find ways to make the volume of that song as loud as possible. Here is one way. Take a phone playing some music and put it in a glass. Make sure the glass is empty, of course. Huh? And suddenly, it's a lot louder. Wow! Why this works is one of the things we're going to be looking at today. So that's what we're going to do today on Science Max Experiments at Large. We're going to learn how to make sound louder, as loud as we can. But I'm going to need an expert to help me. Oh, I know, Michaela from the Ontario Science Centre. She's very smart. All you need to do is go to the Ontario Science Centre and see if she's busy. Yeah, Michaela, it's good to see you.
Nice to see you too.
That was weird. I was wondering if you could give me a hand with an experiment.
Oh, I'd love to, yeah.
It's a sound experiment.
Sounds awesome.
Right on. Okay, we'll take the portal. We'll go back to Science Max headquarters.
Oh, let's take the portal? Cool.
Haven't you taken the portal before?
No, don't you remember it wasn't working last time?
Oh, well, it's
Is it working?
fixed this time. Yeah, no, it'll be great. Trust me. Here we go.
Whoa. Phil, is everything okay?
Usually when I come through the portal, I land on something or something falls on me or...
Not today. It's your lucky day.
I guess so.
Safe landing.
Safe landing.
Nice.
High five. All right, so let's get started.
Okay, cool.
This is the experiment I want to max out today, Michaela. I know. Pretty impressive, right? No, hold on.
Okay.
So I take my phone and I play some music on my phone and it's louder, right?
Check it out. Phil, you've just made yourself a resonance chamber.
A resonance chamber.
A
Very
resonance
nice.
chamber is what we say when we're trying to describe how the sound is amplified. So if the sound's coming in from one direction, it's bouncing around, not really losing energy. So when more sound comes in, that's amplified. We hear it a lot louder.
That's cool. So that's what I want to do. Hold on, let me turn this up. That's what I want to do today. I want to max out as much sound as we can get out of the Science Max theme song, which
I'm
is
so excited.
totally awesome. So what else can we do to do that?
Well, there's a couple avenues I'm thinking. Do you want to try something with electricity or without electricity?
That's because with electricity, we're talking speaker systems and
Yeah.
Right. So why don't we do no electricity for now, and then we
Alright.
can jump to electricity when we feel we've exhausted everything that's non-electric.
Cool. So I was thinking we could try to make a megaphone, because if we have a lot of sound, we could, funnel it in one direction, and then it'll be louder.
Okay.
What do
Yeah.
you
So
think?
the megaphone's pretty easy to make, right? We could just use, in fact, we could use this piece of paper, right?
Yeah, let's try it. What do you think?
I think it's very megaphony. Science taping it up. Okay, ready? Okay, turn it on. Play it. And doesn't sound, but what if I do this?
Hey, there it is. Right on.
Oh,
That song.
yeah? You hear it?
Yeah. Oh, I hear it.
Okay. So that worked pretty well. So,
Oh, yeah, it works. Works well.
So this is pretty easy, right?
Yeah.
Megaphone?
Oh, yeah.
So why don't we max this out? Why don't we make a giant megaphone and see if it makes a big difference?
I think it will. Let's do it.
Sounds good. Let's get started. All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt. The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance. But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look. The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes. So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. Whoa. So Michaela and I are on a quest to make the loudest sound we can. The first step is to make things louder without using electricity. We've looked at a resonance chamber, and now we're going to make a large megaphone. Sounds can be amplified by bouncing sound waves around in a space. When I put my phone into the glass acts as a resonance chamber. The sound waves bounce around inside the glass, and they combine and stack on top of each other. This makes the sound louder. Resonance chambers are used by musical instruments like an acoustic guitar. The wooden chamber bounces the sound waves around, and the sound waves build on each other to make the sound louder. A megaphone bounces sound waves as well. Instead of going off in all directions, a megaphone makes the sound waves all go in one direction. That's one of the reasons why a megaphone makes sounds louder, but only when it's pointed at you. So will a bigger megaphone work better? So we've made a larger megaphone, which is exactly the same thing. You just take a sheet and you roll it up, except our sheet was plexiglass covered in paper, and we've taped it together so it stays. And the idea here...
Oh yeah, bigger megaphone. We're gonna vibrate even more of the air inside of here, and hopefully this thing will be louder.
Okay, so you're ready to try it with the phone?
Yeah.
I think first we should try it with our voices, though.
Okay.
Now, what's your favorite season?
Awesome, I can totally hear you. That's
Can you hear
amazing. And it would be fall.
Oh.
No, Not summer. Spring?
Think
It's
about it.
anything but winter.
So the maxed out Megaphone worked, but we still had to try it with my phone.
Okay.
All right.
Yeah?
Oh, yeah. Oh, definitely.
How about now?
No, not so much. Not so much. Oh, yeah. Nope. Nope.
So that is a
That was
great
cool.
example of non-electrical amplification.
That's right.
Amplified the sounds, no electricity. Okay, bye-bye.
Sweet.
Come on, make some noise! Well, how do you make noise? Well, to know that, you gotta know your sound. All sound is vibration. Here, take a closer look. You see? You got... Okay, let's try this again. All sound is vibration. The string of this guitar vibrates, which vibrates the air around it, causing the sound that you hear. Your vocal cords vibrate in your throat, causing you to make a sound. Ah, 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 la, 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 la. Look at this thing. Look at this thing. See how it's shaking back and forth? It's vibrating. Things that make a high sound, they vibrate faster. Vibrating really fast. Things that make a low sound, vibrate slowly. High note, vibrating fast. Fast! Fast vibrating. And now you know your sound.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big. The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here. This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger, and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud? And yes, this is something you should not try at home. This note makes the glass vibrate the most. Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks. The vibrations were so strong that the glass literally shook itself to pieces. Science! Sorry. Science! Oh, wait. Science! Michaela and I have tried a resonance chamber and a giant megaphone to make sound louder. Now it's time to move on to the next step of the plan, using electricity to help us amplify sound. And that means speakers! So, speakers that you have at home,
3 different speakers here, right?
Looks
3
really
different
busy.
cones.
Yeah, there's a lot going on.
So what's the deal?
Well, here at the bottom, we have a subwoofer.
Wait a minute, a subwoofer.
Subwoofer.
So it's a woofer, the word is woofer,
Yep.
and it's, okay, so it's for dogs, right?
No, a subwoofer is for low notes here in our speaker.
Ah.
At the top here, we have a tweeter.
So it's for birds. It's it, birds, dogs. So low, let me guess, low notes?
Yeah.
Tweeters, high notes?
Yeah, high notes. And then we have this guy here in the middle, and that's called your mid-range speaker.
Oh, that's not nearly a cool name. Now we have speakers, we've taken a look at that, but why don't we take one apart,
Cool.
right?
Yeah, let's do it.
I've got this one here that I spilled juice on, so it doesn't work anymore. So I've kind of taken it apart. So
Cool.
it's got,
Oh, man, that's awesome.
okay, so it's got the cover. That's cool. So what I find interesting is there's the speaker and the wires, right? Because it's electrical amplification. But check this out. This is just a ring to hold that on. And the rest is just an empty box.
We know what that is. Resonance
chamber. That's right. So that's why it's an empty box. So
Let's take this apart too, see what's going on.
So that's the paper cone, right? So that's that's the drum, I guess. It's like the eardrum, the thing that vibrates.
Yes,
Yeah.
this little thing vibrates.
So that this whole thing-
That's for electromagnet. When we turn this on, the electromagnet goes on and off, and it's causing this whole thing to vibrate.
So that's how it works. It's the electricity turning the electromagnet on and off.
Exactly.
And it's on and off and on and off and on and off and on and off. And then it makes it vibrate at certain speeds, right? Hertz. The number of times it vibrates per second is hertz. What we could do is we could max it out with the speaker and plug the phone into the speaker. But this step does not feel like Science Max to me because anybody can do that, right?
Yeah.
You can just turn up your television right now, and that's pretty much the same kind of thing. We need electrical amplification, but maxed out.
Max it out. What are you thinking?
Okay, so I've got a friend, and he's got a stereo system that he built, he put together, and what he does is he tours different cities. So he said he'd bring it by Science Max headquarters.
He's gonna bring it here?
We gotta go outside.
We can see this thing.
And it's very loud, so we have to go outside.
When's he coming?
Right now. All right, let's go check it out.
Seeing sound vibrations is fun.
This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds.
I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then, tape it so it's nice and secure.
Then what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water.
I've got some yellow cornstarch and some blue cornstarch.
This experiment works the best with low notes.
I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume.
It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. Science!
So Michaela and I are going to max out sound. To do that, we need a maxed out sound system. Isn't it amazing? This is gonna be super maxed out sound experiment. This is James, Michaela.
Hey, James, how are you?
Thanks for coming, buddy.
Nice to meet you.
So, tell us about your speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Wow.
So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that
better when you have a van like this?
With a car audio van like this, you want to play low notes. Like your house stereos and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of
Yes,
thunder,
very
kind
low.
of blah, 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 blah,
Yeah.
where you really feel it.
Yes.
Like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much.
I'm totally jealous of your long hair.
Yeah, you need to get longer hair.
Okay, hold on. I'll go right.
Okay.
Whoa! Science Max, experiments at large, super sound!
High fives. Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
At the bottom.
I can't reach it.
So that's great.
Wait. Almost. No, I can't.
Okay, I got my hair protection on. You got your hair protection on?
What's that?
Hello? Oh, hi, Mom. No, I'm shooting the show right now. I can't. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about storing energy and releasing it.
Yeah. Let's try it out for real.
Storing it in a giant spool racer, plus a domino chain reaction, mousetrap chain reaction, popsicle stick chain reaction, and more. All on this episode of Science Max Experiments at Large.
Okay, 3, 2, 1, go!
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. Wow, I really need some more energy. Fortunately, I have some saved up. Ah, that's better. Yeah, I know what you're thinking. Storing energy like that doesn't make a whole lot of sense, but you can store energy, and that's what this episode of Science Max Experiments at Large is all about. In fact, I'm gonna store some energy in this container simply by putting it up here on the top shelf. More on that later. But right now, let's look at another way that you can store energy and release it in a really fun way. We're gonna make a spool racer, and it's pretty simple. Here's all you need. You need some science ribbon. Now, if you don't have science ribbon, you can use regular ribbon, but the ribbon really isn't important. It's the spool that's important.
You'll also need a washer, elastics, pencil or pencil crayon, popsicle or craft stick, and science tape.
Science tape is the same as invisible tape, except I use this one only for science. Here's how you build it.
Break the popsicle stick so it's smaller than the diameter of the spool. Then put the elastics on top of the pencil and pull them tight. Thread the popsicle stick through and feed it all through the hole of the spool. Grab the elastics on the other side and pull out the pencil, and everything will be threaded perfectly. Then stick on the washer and thread the pencil through. Finally, tape the popsicle stick down so it doesn't move.
And if any of these steps are a little too fast, don't worry. All of the instructions are up on the website. That was cool. I I can't make it go away. I can only make it come up. So there you go, a spool racer. And here's how it works. You spin the pencil around, and that twists the elastic. Now that elastic is gonna wanna unwind, right? So just keep spinning that pencil around until it's good and tight. And then when you put it on the ground, the pencil's gonna wanna unwind, but it can't because the table's in the way now, which means that the energy is gonna transfer to the spool, which is gonna turn, whoa, and it's gonna drive away. Yeah, let's try it out for real.
So why does this work? It works because the elastic is coiled, right? Yes, and because I'm putting in the energy to twist it. You see, I'm putting in effort to spin this pencil crayon around, and then when I've finished, all of my effort has been stored in the elastic. When I let it go, my energy transfers
Into movement. So that's, that's what we're gonna do today, Science Maximites. We're gonna max out the spool racer. I think Anthony would really know how to help me with this. So I'm off to the Ontario Science Center. Come on. What happened?
You okay?
Anthony.
Yeah, hi.
Oh, were you in the middle of something?
Don't worry about it. Yeah.
Oh, okay. Sorry about that. You know what I was wondering? If I could get your help with something.
Sure, yeah.
Yeah, one word. Spool racer. Actually, that's two words. Spool racer. Yeah. You want to help me max out a giant spool racer?
Yeah.
Awesome. Let's go back to Science Max headquarters. Okay, Anthony. Today I want to max out the spool racer.
Awesome.
Right? So you twist up the elastic and it goes from potential energy, all stored, to
Kinetic.
kinetic energy. Whoa, there we go.
Awesome.
So,
Okay.
Not too hard to design. Should be fairly easy to
Yeah,
max
really
out.
simple couple of parts here. We just got elastic band inside.
Yep.
And then this big long pencil to store the energy and then release it.
And the most important part
Is spool.
is the spool.
Exactly.
And I know where we should start.
Where's that?
Right here. This is an industrial cable spool. So the big, thick electrical cables, they come wound on this thing.
Yeah, okay.
So I figure we start with this.
Got
right?
it.
And the good news is that it's got a hole already. And check it out, it rolls really well, right?
Uh-huh.
Okay, cool.
Okay.
So, bungee cord.
Yep.
And long pole or something.
Yeah.
And we're ready to go.
I guess let's get some parts.
Okay.
Okay.
Oh, hey, how you doing? You want to buy something? I got a lot of stuff here, and I got a special today only. Potential energy, huh? I will throw in some potential energy with any order. You see this stuff on the shelves here? The stuff on the higher shelves has more potential energy than the stuff on the lower shelves. Don't believe me? Here, hold on. Look at this state-of-the-art traffic controller. Right now, it's sitting up here on this high shelf. Now, if it were to fall, it would be going fast, which means it would have a lot of kinetic energy. You see, when it fell down, it had enough kinetic energy to completely break itself apart. Yeah, well, that's the difference between potential energy and kinetic energy. Look at this bagel, just sitting here, not moving, minding its own business on top of this ramp. It's all potential energy and no kinetic energy. And when it gets to the floor, it's all kinetic energy and no potential energy. Woohoo! And now it has neither because it's on the floor and it's not moving. 5-second rule. And now you know your energy. So what do you say? You want this thing? Tell you what, I'll give you a discount because you know it's gently used. Hey, I'll even throw in this bagel, huh? Also gently used. Anthony and I are maxing out the spool racer. We start with a long coil of bungee cord, which is kind of like a giant elastic, and feed it through the spool. Then we put on a big piece of plastic to act as our washer and use a long pole as the pencil. We flip the spool on its side to wind it up. Then we flip it back and it's ready to go.
All right, so we have it all wound up and we're ready to try it again, but with one change.
Phil,
Yeah,
what's with the trike?
I ride the trike.
It's like I always say, what's the point of building something big if I can't ride it?
There's no way you're gonna fit on this thing.
No, I don't put my feet on the pedals. I put my feet here on the back, right? And then-
Okay, yeah, I get it. You got it?
Hold on, I gotta do my helmet up.
Safety first. You ready?
I'm on it.
Okay, 3, 2, 1, go.
Oh, it's working.
It's working. Amazing.
All the stored energy in the bungee cord is being released and the spool starts to turn. There's even enough energy that I can get pulled along behind it.
It's not going that fast, though.
No, and
It's pretty good, though. It still pulls me, right?
Yeah, pretty good.
So, Spool Racer, actually able to get pulled by it.
Yeah.
You know what? I think we can go even bigger.
Bigger.
Yes.
Well, what did you have in mind?
I'm glad you asked. Yeah!
What is this?
This is an industrial cable spool, and this is the biggest size that they make. And I thought we would do the same thing with this. What do you think?
I think this could generate a huge amount of energy.
Okay, so all we gotta do is just build it just like we built that other one.
Just bigger.
Except way bigger. Let's do it. When you set a domino on its end, you're giving it potential energy because it can fall. Ooh, and when you put two dominoes together, you can start a chain reaction because that one will fall into that one. But it's a lot more fun with more dominoes.
Setting up a run of dominoes is a lot of fun, but it takes a flat surface and a steady hand. And if you want to do it yourself, add gaps, so if one part falls, it doesn't take out the whole run.
Last one. There. I had some dominoes left, but I did it. I made the Science Max logo. See?
Science
right?
Max!
Sort of. Let's see how it works. Ready? Yeah! Now it's time to max it out. Giant maxed out dominoes! Woohoo! Even though these dominoes are giant, they're still gonna work the same. They're standing up on their ends, which means they've got some potential energy. And when I give this one a push, that potential is gonna turn into kinetic energy, and it's gonna knock the next one, and the next one, and the next one. I hope. I don't know what's gonna happen, but let's find out. You ready? Okay, 3, 2, 1. Giant dominoes! Yeah, science! The problem is, when you use dominoes this big, setting them up again is a real chore. This is a mousetrap, but don't worry, no mice are gonna be harmed in the making of this episode. Mousetraps are a great example of stored energy. You see, in order to set a mousetrap, you have to push this bar back, and it's hard to do because the spring holds it. And then you set the mousetrap by putting this little lever underneath this very sensitive trigger, and once you have it set, all that energy is stored as potential energy, but it'll go off with just the slightest touch, releasing the energy. So what if I had a number of mousetraps and they're all set and all of that potential energy is stored up, and I dropped a number of ping pong balls on them? Well, then I could set off a chain reaction where one mousetrap flies and hits another mousetrap that hits a ping pong ball, and then they all go. Now, this is something you can try at home, but do not set the mousetraps yourself. It can really hurt if it snaps on your fingers, so you should probably ask an adult to help you, and then you can see how brave the adults in your house are. Okay, you ready? Here we go. Mousetrap chain reaction. And last one. There we go. And now, let's max this out. Let's do it with 90 mousetraps. and this is a crate of ping pong balls. So let's see what happens when we put them together. There you go. Maxed out ping pong ball, mousetrap, chain reaction. Awesome.
Ready?
I'm on it.
Anthony and I have built a large spool racer.
Oh, it's working.
It's working.
And it worked so well, the only option was to go bigger.
This is an industrial cable spool, and this is the biggest size that they make.
I think this could generate a huge amount of energy.
Building our giant spool racer is the same process as the other builds.
So the steps are exactly the same, but on a larger scale. And this time, we're gonna use, obviously, the large spool, and we're gonna use this 2x4 as our pencil windy thing.
Coil some bungee cord, feed it through.
Ready?
Yep.
Okay, here it comes.
There we go.
Got it?
Haha, yeah.
Add a washer and a long 2x4 to act as our pencil.
And now we stick the giant 2x4 inside the coil.
Just about. Yeah, we got it.
There we
cool.
go.
And we're ready to try it out.
So it looks like we're ready to go.
Yeah, exactly.
Do you want to do it in here or you want to do it outside?
Oh, definitely outside.
Okay, let's go.
Yeah, okay, cool.
Yep. Oh, it's heavy. Batteries are great at storing energy. They store electricity. Batteries. But if you're like me and you have a whole bunch of batteries and you don't remember which are the good ones and which are the dead ones, there's a trick that you can use to find out. Get a frying pan or a brick or a concrete floor or something else that's very, very hard and an adult's permission. Here's the secret. Dead batteries will bounce and batteries that still have some life in them won't. Watch. Good battery. Dead battery. Now, it's a little hard to see, but listen. 1 hit, 2 hits. Here's what's going on. See, batteries store electricity in the form of a gel, sort of like modeling clay. This is modeling clay, fresh from the fields, where the pits, the mine, wherever modeling clay comes from. And this is modeling clay I've left out for about 5 days, so it's all dried up and hard. Now, when modeling clay is new, it's all wet and soft, and when you drop it, it doesn't bounce very well. I've left this piece of modeling clay out to dry for about 5 days. Now it's all dried up and old, and it bounces. New, old. So, same thing with the battery. Good batteries won't bounce, and bad batteries will. Science. Here's a fun chain reaction you can do with popsicle sticks, or craft sticks, because these ones are a little bit wider than popsicle sticks. It is because these kind of sticks are slightly bendy, and when you bend them and put them together in a pattern in a certain way, you can keep them under tension, and then they want to snap back, and then they'll fly. So here's how you make the pattern. Ready? You take a popsicle stick or a craft stick, and you put it down on the table. I know, okay, it's a slow start. And we take another one and put it across. Now comes the secret. The secret is over and then under. You want to put it over one and then under another, like that. And then this one, over, under. Put it over the one that looks like it's the top stick and under the stick that looks like it's the bottom stick. And then it starts to hold tension. It starts to hold the potential energy.
Continue this pattern. Each stick goes over and under the 2 sticks at the end.
Now here's the trick. Soon as this one lets go, then that one will let go, then that one, then that one, then that one, and that's how you get the chain reaction. They all start flying up. So you have to build it with never letting go of that last stick. You gotta always remember to keep a hand on it, or else you'll have to start again. So, okay, so you ready? You wanna see me let it go? Here we go. I know, that isn't so great because it's better if it's a longer chain. So fortunately, I have a longer chain. I've got a binder clip on this end, keeping the craft sticks together. Ready? 3, 2, 1. Wow! Release of kinetic energy from the potential energy of winding all the craft sticks together. Fun, and you can totally do it at home. Now, let's max it out. Behold, almost 800 craft sticks in a long, nicely designed triangle. Ready? 2, 1. Yeah! Craft stick chain reaction. I'm gonna go get something to clean this all up with.
All right. Anthony and I have built a giant spool racer and have taken it outside to try it out. In order to wind it up, we flipped over the last version on its side. But this spool weighs 200 kilograms. Easy to roll, almost impossible to flip over.
Come on, get it.
I don't think it's gonna work. It's too heavy to move.
Yeah.
We should have thought of that before.
Well, I'm sure we'll think of something.
So Anthony and I thought about it. And thought about it. And thought about it.
I got it!
What?
No.
But you,
And the answer finally dawned.
what if we roll it this way? Because then that would wind it up, right?
That's brilliant!
By rolling it backwards, we wind up the bungee cord in one direction, which will make it want to unwind in the other direction. Anthony and I roll it across the parking lot to get it wound up tight.
I don't think I can hold it anymore.
Okay. Okay. Let go. Okay, it's wedged.
It worked.
All right, one more thing. We're gonna hook the trike up to this one as well.
Okay.
Okay. So right now, it's all wound up, and when it gets moving, the potential energy in the coil will turn into kinetic energy. Now, just in case you're tempted to try this at home, I need to tell you, do not try this at home. We're trained professionals, right?
Yes.
Yes. Well, as much as anybody can be trained for this, because no one really does this.
Are you ready?
Ready?
Okay, here we go.
Whoa. It's working!
It's working!
Yeah!
Sure enough, all the potential energy we stored in the bungee cords starts to unwind, which rolls the spool and pulls me along behind it. What's more, that big heavy spool has a lot of momentum. So when it gets going fast, it just wants to keep moving. It wasn't long before I had to jump off.
Amazing!
All right, that had a lot of kinetic energy.
That was a ton of kinetic energy.
There you go, Science Max, Experiments at Large, massive spool racer. Your turn next?
Yeah!
Okay. So that's what we're gonna do today, Science Maximites. Whoa! We are going to learn how to juggle. I can't hear you, I've got dominoes in my ears. And you put it in, and whoa, and now it's all broken. Well, here's a trick. Here's the trick. It's me disappearing. You see? When it would, blooper reel? Blooper reel.
Okay, hi.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large.
Science Max!
gravity.
Gravity!
Gravity! Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party! All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Look straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it to make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. We're gonna, oh yeah, I gotta clean that up. We're going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right. Here I go. Aha!
Oh, hi, Phil. Yeah, what? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To replace the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa!
Gravity defy. Gravity defy. Gravity
Look at it fly!
defying.
Okay, not exactly, but What if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why.
When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it.
Until there's no more tension, and then the top passes the bottom and the whole thing falls. That is how it works. But here is the real question.
Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring!
Let's max it out! Bring it. Don't tangle it. So now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go!
A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it.
So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa.
Sonia and I are maxing out the hoop glider out of bigger and better materials.
This is the largest tube I have, right?
A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and...
Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited.
we take our plastic and metal hoop glider outside to test it and...
Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it?
Sonia and I made a very solid design, but the problem with it became pretty obvious.
Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down, so you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere, and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon, and it had a, there. A giant balloon And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Gravity. Gravity. Gravity makes things fall. Well, where do they fall? They fall down. Oh. Towards the center of the Earth. Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes. Gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy. Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground.
it
I
falls.
see.
So we need something that's light
Light
and something that's strong.
and strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out. Hoop glider dance! Okay, 3, 2, 1.
That's pretty good!
That was
Pretty
amazing!
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good!
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it. Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I made this, made a slightly heavier one.
Let's do it.
Okay, 3,
Yeah.
2, 1, go! Not bad. My turn.
Here we go.
Okay. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome!
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But
think
I
we can
think
make
that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's
All
do
right.
it. This is an egg. Eggs do not like to be dropped.
Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over. Good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well,
That was
Pretty
amazing.
good. Here we go.
but we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more can you ask for?
Well, it's my turn.
Hey, see you next time.
I'm the marker.
Take 8. My goodness.
I play the wobble,
Wobble.
the wobble.
Forgot my line. Forgot my line. Going back down.
Wobble, 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 wobble.
Hello? Hello? Hoop glider central calling. Yes? You were having problems with your hoop glider? Oh, what's wrong with it? Oh, you're using it as a phone? Yes, well, that's your first mistake, yeah. Today on Science Max, I forgot to tell you my name. My name is, I'll do it.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is all about vibration and frequency. Frequency and vibration. What's the difference? We build a maxed out Vibrobot, spin a giant disc, suspend water, and play with lasers. All on this episode of Science Max, experiments at large.
Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulum. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And okay, we're gonna be building. Whoa, okay. We're gonna be building this little guy. This is a Vibrobot, and he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a Vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a Vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors. This kind of tape is called electrical tape. Science tape, which is the same as invisible tape, but of course I use this tape only for science. And some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary. I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own Vibrobot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your Vibrobot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you want to do is take your plastic drink bottle cap and make a hole with a toothpick. You want to make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's going to give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the Vibrobot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now finally, we're going to attach the eyes. We take some science tape and we put the straws over here. I am Vibrobot. I am here to vibrate. Take me to your leader. So then you attach your tape with the wire to the top of the battery there, and then the other wire to the bottom of the battery, just like that, and let your Vibrobot make some art. Now, if the battery is new, your Vibrobot might be jumping up and down quite a bit. So you can do what I like to do and add some more weight, and then you make better lines with your Vibrobot. And your Vibrobot makes art. How long will he last? Probably till lunch. And there you go, Vibrobot art. Art made by a robot. How cool is that? So that's what we're gonna do today. I'm gonna meet Chris from Logix Academy, and he's gonna help me max out the Vibrobot. Plus, we're gonna learn a little bit more about vibration. Come on. Oh, hey, Chris.
Oh, hey, Phil.
Thanks for coming.
My pleasure.
Okay, here's your Science Max lab coat.
Thank you.
So you guys at Logix Academy, you also build a Vibrobot, right?
That's right, we do.
This is mine, and it works pretty well.
That's awesome.
So, I want to max this out.
Cool.
So I thought we would start with, instead of this motor, we would start with this motor.
Wow.
It used to be a round circle, but I cut it off so that it's off center.
Perfect.
I've also got, this is our battery.
Fantastic.
That's as far as I've gotten so far.
Well, it looks like we need a frame next.
Right, something to be the cup.
That's right.
So we just need some sort of larger cup.
Ooh, how about that metal shelf over there?
Oh, this thing?
Yeah.
This is just something I keep my parts on.
It's perfect.
Really?
Yep, the shelves will house everything that we need, and it looks like it'll be strong enough to hold everything together.
Now, the Vibrobot had markers on the bottom of it.
That's right.
To make a little pattern. Should we try that with this?
Because we're going bigger, what if we used paint and paintbrushes instead?
Okay, sure. We could attach paintbrushes to the legs. Pass me one. All right, so now all we need to do is get some paint and some paper.
That's right.
And we can fire it up. Okay, let's move it over this way.
Vibration and frequency. What's the difference? They're all connected. Ta-da! Now, whoa. Vibration is things going back and forth. Back and forth. And back and forth. It's a cycle. Cycle, 25 bucks. Oh yeah, it's the wrong kind of cycle. Never mind. Well, if that's vibration, then what's frequency? Well, frequency is a measure of how fast or slow, how frequent those vibrations happen. Look at this bowling ball. Look. It is swinging back and forth, but not very fast. You could say it has a low frequency. We measure all kinds of things by their frequency. This thing is terrifying. When you turn the dial on your radio, you're tuning in to different frequencies of radio waves. Hey, look at this punching balloon. It's going very fast. You could say it has a high frequency. So, now you know. Vibration is something going back and forth, and frequency is how quickly it does it. Ramona, the bowling ball keeps coming through everything. How do you turn it off? Okay, back to our main experiment. Chris and I are taking a Vibrobot and maxing it out. We have a large motor and a battery, and we're taping it all to some shelving. Just like our small Vibrobot, our motor needs something to make it unbalanced when it spins. That's what will cause the vibrations.
It's just taped. I haven't attached it in any other way. Do you think that's okay?
As an engineer, I have superior faith in duct tape.
Okay, well, that's good to know.
We're also adding an on-off switch and some paintbrushes on the bottoms of the legs so our maxed out Vibrobot can make art just like the small one. The final step, dipping the brushes in paint and setting it on a big piece of paper. We fire it up and it immediately shakes everything off the shelves.
It totally spilled all the stuff on the shelves.
The motor shakes the Vibrobot a lot. But there's a problem. All that shaking is starting to take its toll on the shelves. The wheels come off, the screws come out, and finally...
Whoa. It totally shook itself apart.
Destroyed itself.
The shelving unit just completely falls apart when it's being shaken.
Vibration is really hard on the structure of an object. We need something more sturdy, something that can take weight.
Steps, maybe?
Yeah.
Okay, hold on.
Okay.
Okay.
Yeah, this looks much better.
Okay, great. So we build the new Vibrobot out of this. So more paint brushes,
Bigger motor, more paint,
more everything.
more everything.
All right, good. This is a pendulum. It's just a weight suspended on a line and anchored from above. Pretty simple. Pendulums were used for hundreds of years for all kinds of reasons, but most famously in clocks. Why were pendulums used in clocks? Well, here's why. Let's mark every time the pendulum hits the bottom of the swing, right here. Okay, watch. All right, now here's the question. How fast will the beeps be if I swing it from much higher up? Let's find out.
No matter how high the pendulum swings, it keeps the same frequency. That's why they were used in clocks, because it could swing for a long while, and even though it would lose energy, it would still keep perfect time. The frequency of a pendulum doesn't change, no matter how high it swings or how much weight is on the bottom. The frequency comes from how long the line is.
Now this is a pendulum wave.
Because each bowling ball has a line that's a different length, they have a slightly different frequency. They start out swinging together, but soon they start to make interesting patterns. Remember, each pendulum is keeping its own perfect time, even if it's slowing down. It's only the length of the line that gives each pendulum a different frequency.
And now we're gonna max it out with well, I guess these are already bowling balls, so this is already pretty maxed out. I'm just gonna leave that there. These are balloons. This is a laser, and these are awesome laser safety glasses. Now, lasers are made of light, and light has a frequency. In fact, each color of light has a different frequency. This is a red laser. Check it out. Yeah, cool. This is also a very powerful laser. Oh, I can pop the blue balloon with the red laser because the blue absorbed the red light from the laser and then it heated up and the balloon popped. But here's the cool thing. I cannot pop a red balloon with a red laser because the red balloon reflects the red light from the red laser and I can't pop it. If I wanted to pop a balloon with a red laser, I need to use a darker balloon, one that absorbs the red light, like a black balloon. So there you go. Lasers, frequencies of light. I'm gonna keep this red balloon because it's always nice to have a balloon.
Chris and I are maxing out the Vibrobot, but our last version shook itself apart. Now the plan is to start with something more solid and try again. We found some very solid steps and added an even bigger motor, an even bigger battery, and attached a half-circle wheel to make the vibrations when the motor spins. We add some paintbrushes and fire it up.
Here we go! Come on!
Go, Vibrobot!
It wants to move.
Is it moving at all? So it's still not working. It's sort of getting caught in the paper, and it's on the paintbrushes.
And the paintbrushes seem to be absorbing too much vibration, and then the paper's stopping it as well.
So why don't we remove the paintbrushes?
Yeah.
And we might as well remove the paper if we don't have any more paintbrushes.
Yes.
And we'll see what happens.
We'll see what happens.
Okay. No paintbrushes, no paper.
Okay.
Now let's try it. 3, 2, 1, go!
Yeah! Aha! It's moving. Not bad.
The shaking is good, but I don't know if the shaking is enough. So what do?
Well, we could add another battery.
Another battery, which would give it more power?
That's right.
Okay, let's try that.
Okay.
Okay, so it wasn't working before.
No.
Not enough power. And now we've got a second battery here.
That's right. We've wired them up so that one power feeds into the other, so we've got twice as much juice as we do.
So it's just a matter of clipping this onto there.
That's right, but hold on.
Yeah, safety glasses, because now we don't know what's going to happen anymore. Ready? 3, 2, 1.
The extra battery makes a big difference. The new Vibrobot shakes around and only shakes itself apart a little.
All right, that was amazing. Okay, so all we needed was more power.
That's right. I think it didn't have enough power to vibrate up and down, and that's why it wasn't moving every time it hit the ground.
So I think if we're gonna use this much power, I think we need to build it again.
Okay.
Build it even stronger and with a bigger motor.
Yeah?
And more power. And then maybe I ride it. You think we can build that?
Of course.
Of course. Okay, let's do it. You want to see something cool? I can make this water levitate, defy gravity using the power of science. You want to see? Behold! Gravity-defying water! I can even make the water go very slowly. Or I can make the water go back up into the hose. Or I can make the water completely stop. You know what's interesting? The water does not seem to be stopped for me. You see stopped water because you are looking at it through a TV camera. See? Real life, TV camera. Real life, TV camera. You see, movie cameras and TV cameras take a whole bunch of still photos and then run them together really, really fast. 24 times a second for our TV cameras. I have created a device that drops water at 24 times a second, and what happens is everything lines up. So it looks like the water drops aren't moving. But watch this. I grab the hose and it's fine. But I let it go, and the hose is vibrating back and forth at exactly the same time the camera shutter is going back and forth, and everything looks like it stopped. The power of frequency has defied gravity. Okay, so not really. It's kind of a camera trick, but I prefer to call it science. Here's a fun way to play with things going back and forth. This is Euler's disc, and it's designed to spin like this. What's going on is friction and gravity are slowing that down and pulling it towards the Earth. Now, you don't need a fancy disc like this to do this at home. All you need is a pot lid. Check it out. When the pot lid spins, friction and gravity start to slow it down, which means each spin gets lower and lower, and the frequency gets higher and higher. But the difference between a pot lid and Euler's disc is Euler's disc is made to go for as long as possible. The heavy puck has a slightly rounded edge and sits on a glass surface that is slightly concave, like a bowl. All of this is designed to make Euler's disc last a really long time, which is quite a while. But eventually, friction and gravity pull the disc down, and finally, it stops. Pretty amazing, right? Well, wait till we max it out. This is Trevor, head of the Science Max build team.
Hey.
Thanks for setting this up, Trevor. So what is this?
This is a giant side of a spool, big hydro spool.
Okay, so this is the largest disc that we could totally find, and we've got it all hooked up here We lift it up, we spin it, and then you pull the thing and it will drop down and spin like a coin, because it's the only way we can do that with something this heavy.
Yeah.
Ready?
I'm ready.
Okay.
Trevor and I hoist it up and get it suspended above the ground. Then I start to wind it up.
Ready?
When it's going fast enough,
And go, Trevor!
Trevor pulls the release and it turns out a 200-kilogram spinning disc works exactly the same. As it spins and rolls, gravity and friction work on it, and the frequency speeds up as it gets closer to the ground until it stops.
Giant Oilers disc. Nicely done, Trevor.
That was awesome.
That was great. Let's do it again.
All right.
Our Vibrobot was working well, so that means it's time to make it way bigger. We started with a big metal table and added a huge motor, one 20 times as powerful as the last one. Instead of batteries giving us 12 volts of power, we're going to use a plug, which is 10 times more power. We've added an off-center wheel for vibration, bolted the motor to the frame, and added a protective cage all around to prevent anything from flying off. It even has a seat for me to ride.
Okay.
Okay.
You ready?
Ready?
Here we
We
go.
fire it up and it's very shaky.
Oh, wow. Wow. That was really uncomfortable. It was like very bangy, even with the seat.
Yeah?
I'm gonna try standing on it.
All right.
When I try standing on it, the Vibrobot lives up to its name. It vibrates all around the lab.
Oh, wow. My legs are numb to the knee.
I'm not surprised.
Vibrobot!
All right.
Yeah, that worked really well.
That was awesome.
I really can't feel my feet right now. And it held together, which is impressive.
That's right. The more power and the stronger structure paid off.
Yeah, the only thing I regret is not getting a chance to... Wait a minute, come with me. Okay, so I achieved my dream of riding the Vibrobot.
You did.
But we never got a chance to make art, so we've dipped a whole bunch of nuts and bolts and heavy things in paint.
Yep.
And now we're gonna turn on the Vibrobot and see if we can make some art. Let's see how it looks.
Oh, wow.
Ta-da! Vibrobot art. Vibrobot has been a huge success, and we got some art to keep. High fives. Well done. Science Max, Experiments at Large. Who gets to keep the art?
Rock, paper, scissors.
Okay. 1, 2, 3. Okay, tie. 1, 2, 3. Tie. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. Ah, tie. 1, 2, 3. Man! There's gonna be a red balloon, but those red balloons are gonna be pushing this way, and then this afternoon we're gonna have this blue balloon, which is quite nice. Over to you, Kathy. Thanks, Kathy. Science! I figured we would have maybe a bigger motor.
Yes.
Or a bigger, no, I'm gonna try that again. All thrusters ahead. Whoa! Balloons. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Today, I'm maxing out the power of water. Water is very heavy. Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car. You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom. Trim them down, maybe about that much. Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and do the same thing on the other 3 sides. Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base. Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside. And don't forget your safety glasses. Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it, and kink the straw, and woohoo! Woohoo! Haha, there you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony,
Phil?
I'm here.
Whoa, Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
Okay.
today,
Yeah.
I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda,
Yeah.
and you pressurize this container, and,
Okay.
and the water shoots out that way. So the car goes this way.
Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your
Okay.
stuff. This
Okay.
is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole
Yeah.
and weld them on. I don't know if that's...
Something tells me this wouldn't work, so we
Okay,
need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So
Yeah.
we'll reuse it. Yeah?
Okay, you know what I'm thinking
Yeah.
now, though? I know
Yeah.
this the problem is I think this is like an oil drum, right?
It is.
And,
It's an oil tank from a house.
and these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower
That
or
makes,
something like that.
So all we need to do is get a pressurized water tank,
Okay.
put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All
yeah,
right.
let's get to it, man. Okay. we
I
need
got
to-
some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me. So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we
So I've joined Anthony and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Haha! So, water car, maxed out version,
Huge.
water tank.
And filled with lots of water and lots of air. too. Yeah. Pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it. Okay.
Okay, here we go. 3,
2,
1, go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That's amazing.
So, pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So,
because then it would be too heavy, right?
exactly,
Much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water,
Okay.
and then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water,
right?
and I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah. All right. Amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out.
The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of?
Power washer pumpkin carving.
The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home.
Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate.
Oh, no, not Overwhelmo.
Did someone say Overwhelmo?
No, wait, no. Next. Oh, not that. Okay, good. Okay.
Behold, it is I, Overwhelmo!
Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the hot trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes?
Is that it?
Yes?
Well, it's not magic.
It is defying gravity.
Nope.
The water would fall and the card would fall to the floor.
It's not magic.
This is magic.
No, it's science.
Horse feathers.
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Balderdash!
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes.
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the... No, that's not my music. Hold. You will rue the day when... That's not my... Hold. Overwhelmo shall return.
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car! Amazing! Is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump. That's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump, and we're ready to go.
So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Nothing happened. No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way. That's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it down
at the, yeah, exactly.
like that.
And then
at the paddle wheel, and then the paddle wheel spins, and that propels the car.
Exactly.
Right?
Right.
Okay.
Okay, well,
We can do that. Let's do it.
sounds good,
We'll
yeah.
put it together. You know what? I have a paddle wheel because I had a failed hydroelectric. This is called flyboarding. Whoa! Powerful jets of water are being shot out from this board at my feet. Whoa! The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well, we don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform. Woo-hoo! Flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it. It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo! Our maxed out water car didn't work so well. The main reason is that that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go. Okay, so here's the latest version of the water car, Water Wheel!
Yeah.
All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan. Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it.
And Phil,
Yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to.
Even half full, you
Even
can't
half full,
move
I
it.
think we need less fuel than we gotta get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never
Okay.
moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go in its own.
Exactly.
Okay.
You wanna get it
Yeah,
down?
absolutely. Let's do it. We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference.
Yeah, it's working!
The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going! All right! Amazing! Yeah! Look at it, man! This thing worked like a beauty.
It worked all, it went all the way. That
Yeah.
Way to go. The water car, finally a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely.
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.
Ah! Let it go and...
There we go. Oh, careful.
I can't really see with my goggles.
Behold the power of physics. Yeah.
The door's full.
This is called foot. Whoa! All we have to do is wait.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about generating electricity.
Where do we get this electricity that we use all the time?
We try to generate as much as we can using human power, plus solar energy, tidal energy, wind energy, and more. All you need to do is turn the generator. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape.
It's the same as invisible tape, except I use this one for science.
A cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because Today on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Oh, Anthony! Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So you think this is a good size?
I think this is a great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
To red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and I'll turn the generator.
Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach to the end of the generator so we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5.
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is the generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out. It goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that? and we move the conductor past it like spinning. It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. One on either side, and one on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works.
Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand,
It is now a stationary bike. It'll be even more stationary once we screw it down.
and attaching the generator.
All right, the bike generator. Bike-orator. What should we call this thing?
Bike-nomator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get one revolution here means a whole bunch is spinning
Exactly. The
there.
more we get here, the more our generator spins, and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill.
It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay, well,
Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang on a sec. I got it.
And maybe we should attach the horn to the next thing too.
Turn it off.
So you want to generate some electricity. But what do you choose to generate that electricity? Hydro? Nuclear? Coal? Solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator.
Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you want to come and give me a hand over here? My arm is getting tired. Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel. I just sort of put this together, but it works the same way. There are 2 plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons.
Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle, and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set.
Uh-huh.
Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah, from something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That
and
would
then
work.
the rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So, if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelectric? We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da, you're creating electricity with the power of hydro. Ha 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 ha! I did it. Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible. Okay.
Okay.
Crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here. Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, that spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. He's still off by quite a bit. Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas,
coal power.
It's all great ways to generate electricity.
Yeah.
And human power,
not so much.
Not as good. No. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes!
Okay.
Give me,
You take the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up. Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large. So this is a solar panel, and this is a train. You're generating electricity. You're in the way of my solar panel. Oh, no, it's spinning the other way. I forgot a step. The water in the oceans doesn't stay still. The thing in the background, it totally threw me off. What was that? Okay. Where were we? We were... Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass. Now that I'm here, I realize it's really difficult. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. And Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out.
And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh, via the portal?
Yeah, by the portal.
Oh, okay.
You sure? I
yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay. Don't worry about it.
No,
No,
I
no,
think
it's fine,
definitely.
it's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery.
Yes.
More voltage and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet, and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get
to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we were not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was, okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera. So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, let me turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger, and of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on that.
Around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the Electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay.
Work together.
Yep.
Wow.
So that's passed all of our tests.
Yeah.
This is really strong.
Is there a way to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh! Okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top.
And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end? Not really, no. But would you be impressed if I was to balance this coin on top of this coin? Possibly. Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this. And now, I say, a magic word. A magic word! Ha 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 ha! And now, you must let me into your academy. Wait. What's under the cloth? What cloth? This cloth? Nothing! Oh! Is that a magnet? This? No! The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling. No, this is set dressing. It's just... It was a good trick, but it's science, not magic. Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks. We can still see you! No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh. Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got
2 electromagnets, 1, 2.
And those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
we need to keep you safe because you're going to be using these electromagnets to get across this massive beam above us.
That's right. I'm going to stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got a helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
Oh my goodness. What?
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets. Woo! You want to go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Oh, careful. Don't mess it up, Overwhelmo.
Overwhelmo.
Send in the next applicant for the Wizard Academy.
Overwhelmo.
I say, the magic word.
I say the magic word. The magic word!
Well, that certainly does seem like magic, yep.
As I balance not one coin, not two coins. That's a 3.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large.
Science Max!
On this episode of Science Max, I'm on a quest to harness the power of lightning. Its balloon-sticking, hoop-levitating, hair-raising power is all thanks to static electricity. Hold on to your